So, good morning, and welcome back. So, last week we had a mini course called Introduction to Statistical Network Analysis, and I hope you took the material seriously because we now have a mini course that's called Statistical Network Analysis, not an introduction anymore. And this week we have the pleasure of having Jesús Arroyo from Texas A&M as our lecturer. Joshua Cape from Wisconsin will also be in charge of this mini course. Well, without further ado, Jesus, please.
Okay. Thank you everyone for coming to the course. And well, I first want to start saying thank you to the organizers of this amazing workshop. The past week was really nice with a lot of interesting talks and mini courses. And well, thank you, Roberto, for putting together this workshop, and Andresa, Gabor, and all the organizers for the invitation to present here. Yeah, and it's my pleasure to be here with you in Brazil today. So, well, as the title of this slide says, today I'm going to be talking about graph matching. So basically my goal on the next 3 lectures is today I'm going to focus mostly on graph matching. In the next couple of lectures, I'm going to focus on community detection. And I'm going to go a little bit deeper on some of the details that Keith mentioned on his lectures last week, and in graph matching as well. We had a talk last week by Mickey that was really nice, and well, I will go into some of the details of the graph matching problem in this talk. So let me start with a very simple toy example. So, well, what's the problem of graph matching? Let's say I give you 2 graphs, right? So in this case, the 2 graphs are exactly the same, and the graphs are labeled. So every node has a label, and there's a correspondence between the 2 because they are just the same graph, right? So then in the graph matching problem, what happens is that first we hide the labels, so we don't know the labels of the second graph, and then we shuffle the edges, shuffle the vertices. So now the problem is to find the correspondence between the first graph to the second graph without knowing the labels. So, I mean, in this toy example, there's a unique solution. So, I don't have a poll or anything, but maybe if someone wants to guess anything, about this graph or any ideas or who are the correspondences, so please raise your hand or give any suggestions on how you would solve this problem.
You can try all possible.
Sorry?
You can try all possible permutations.
Yeah, actually, that's a great idea. I mean, in principle, you can try all possible permutations. There are n factorial permutations, and because there's a unique solution, eventually you will find the matching, right? I mean, that will take you, in this case, the graph is not too big, so it's possible. But
you can find the max degree.
Right, yeah, that's another option, right? So in this particular case, we can also look at the degrees and match some of them. So for example, let's see.
Cowboy's the bottom one.
Yes, actually, yeah, so this is the one with the largest degree, so these 2 should be the same. And, or what?
It's the bottom left there.
This one? Yeah. Yeah, you can also see that, for example, these 2 have degree 1, so they should be like this and this. But by looking at the neighbors of this one, you can also identify some of the correspondence, right? So, I mean, in principle, we have these 2 approaches. On the one hand, we can do brute force and try all the possible permutations, which is sort of what I'm going to focus on today to try to understand the difficulty of the problem from a statistical perspective. But we are also interested in finding efficient methods to match the 2 graphs, right? So in this case, in particular, we can use some of the properties, look at the degrees or other things, and find the correspondence between the 2. Okay, so, well, this initial problem is called the graph isomorphism problem, in which the 2 graphs are the same. So basically, the idea here is that we observe a graph, GA, with some set of vertices and edges, and a second graph, GB, with the same number of vertices. And there are 2 questions that we want to solve. The first question is whether there's an isomorphism between the 2 graphs, meaning that we can just use a permutation sigma, a function that goes from the set of vertices of one graph to the other graph in order to find a correspondence. And the second question, well, the first question is whether they are isomorphic, and the second question is whether this isomorphism can be obtained, maybe in some efficient way or in some alternative way, right? So these are the two main questions of this problem. In terms of feasibility, well, there's going to be a unique solution as long as there's a unique function or a unique permutation that maps one graph to the other, or in other words, that the set of aptomorphisms of the one graph only has a single solution, meaning that, for example, we cannot identify two vertices that if you permute the labels, you will get exactly the same, a graph that looks exactly the same. In terms of the computational complexity of this problem, well, this has to do with computer science and all this theory about P versus NP and so on. But the most efficient method known nowadays was proposed in 2015, 2016 by Laszlo Babai. And basically, this is a quasi-polynomial time algorithm. So it's not polynomial. It's slightly slower than polynomial. So that's why this cannot be solved super efficiently or in the usual sense of having a polynomial time algorithm to match the two graphs in general. But it's very close to being computationally efficiently solvable. Well, this is for the worst case scenario. You can always find a graph that, in the worst case, is going to have this quasi-polynomial time. But for many specific classes of graphs or random graph models, it's possible to find efficient methods to solve this problem. So for instance, we can consider a very simple idea. So let's say A is going to be the adjacency matrix of one of the graphs, and B is going to be the adjacency matrix of the other graph. So these are matrices of size n by n. So if the two graphs are isomorphic to each other, we can find a permutation Q, or a permutation matrix Q. I'm going to denote by pi n the set of permutation matrices. So basically, pi n contains all the matrices with binary entries such that Q transpose Q is equal to the identity. And basically, what we can do in order to define this correspondence between the two graphs, we can write B as a permuted version of this adjacency matrix A. So basically, what this Q is doing is just shuffling the rows and columns of B. Let's say we have a permutation sigma that goes from n to n. We have that Qij is going to be equal to 1 if and only if sigma I is equal to j, right? So basically, whenever vertex I is being moved to vertex j, this operation Q transpose IQ is going to shuffle rows and columns in the corresponding way, and then we have this isomorphism between graph 1 and graph 2, right? So one particular method to match the two graphs using the eigenvectors of them. So if we write the eigendecomposition of A as B lambda B transpose, for instance, then the eigendecomposition of B is going to be Q B lambda B transpose Q transpose, or actually Q transpose on this side. So one can simply take the eigenvectors of B and the eigenvectors of A. I mean, we just do the eigendecomposition. We don't necessarily know Q in advance, but we can obtain this matrix of eigenvectors. And then we can multiply Q transpose B times B transpose. So this is going to cancel out, and then we're going to get the permutation, right? So that's an efficient method that we can use. However, you can notice here already that this method is going to have some limitations. One of them is what happens when the eigenvalues of the adjacency matrix have cardinality greater than 1, so we have repeated eigenvalues. Then the eigenvectors are not unique, right? So in this case, I mean, as long as the eigenvectors are unique, this method is going to work modulo some signs that may change the entries of B to negative or positive. But, well, I mean, so that's a particular efficient solution. I think this was also proposed by Babai in the 80s. And yeah, so in principle, for the graph isomorphism problem, this may work, but under some scenarios. We can also consider some classes of random graph models, for example, the Erdős-Rényi graph model. And it was shown by both of us in 82 that there is an efficient method to match Erdős-Rényi graphs with high probability under some conditions. But okay, so in principle, there's hope of solving this problem efficiently in some cases under some properties. Well, so I mean, this was just the introduction because the problem that I'm going to focus here today is a noisy version of this problem. And the idea here is that, well, this is a statistical network analysis course. So in statistics, we want to learn something from data. And in nature or technology or other areas, usually the data is noisy, right? So we don't get to observe two pairs of graphs that are exactly the same in most of the applications. And well, in principle, we need models to characterize this noise in some way. And the algorithm should be able to handle this noise in order to match the two graphs. There are applications, for example, in biology, where we have protein-protein interaction networks, and maybe we want to identify proteins across two networks, or brain networks. Actually, I have some pictures in a minute. This is also a popular problem in computer science and in image and video processing, where we can construct a graph from the data, and in some cases, we may need to match the data. For example, could be images, could be correspondence between two different languages, and the nodes can be words. And by looking at the graph and the similarities between the graphs, we can try to identify who are the correspondences between these two sets of objects. And in social networks, this is a popular situation. For example, if you have a Facebook network and then you have a Twitter network, and I don't know, the owner of one of these companies wants to identify the correspondence between the people, maybe to sell products in a different network and use information in one to the other. Well, the networks are not going to be exactly the same because people don't necessarily relate in the same way across different social networks, but we can use some models in order to characterize the noise in these social networks and then try to match the correspondence between the two graphs. So I have a couple of examples here. Well, this is something from computer vision, where we have images. Basically, we can define nodes in the pixels of the image, measure the similarity between nodes, for example, by looking at how similar the pixels are and how close they are in a space, and define a graph in this way, right? So we get a graph. And then when the image is moving, for example, in a video, or if we're tracking an object across two different pictures, this could also be, for example, some MRI taken in a person or something like that. We can find the correspondence by looking at the edges of this graph and try to match them in some way. So that's one particular example. Here, there's also a video of a house moving, and then we can apply a similar idea. So this image is taken from this picture about linear graph matching in computer vision applications. Here's an example of a brain network. This is data that was recently published in Nature. It's from Drosophila brain. So basically, the Drosophila is a very small fruit fly. It has a brain with about 3,000 neurons in total. So recently, scientists were able to map all the neurons into a network and find all the connections between these neurons. So what you can see here in this picture is the adjacency matrix of the brain of this animal. On the top left, we see the connectivity between neurons in the left hemisphere, and the right bottom, we see the connectivity between neurons on the right hemisphere. So scientists are interested in understanding the relationship between the two hemispheres of the brain, maybe to understand how the functionality changes in one hemisphere and the other. And the first question to ask here is whether we can find a correspondence between the neurons of the two graphs, right? So once we have the correspondence, we can compare the two sides of the brain more easily and maybe find regions that are more similar or more different and so on. But before doing that, we need to match the vertices once the data was collected. So this is something that was, the matching process of these two hemispheres of the brain was recently done by a group of people at Johns Hopkins. And basically what they did was solve this graph matching problem, and they were able to identify more than 90% of correspondences between the vertices of one hemisphere and the other, which were about 1,500 vertices on each hemisphere. Anyway, so these are examples of applications. And, well, one important thing in both situations is that the matching is not exact, in the sense that in the brain, we may see differences between the two hemispheres. So we shouldn't expect to see exactly the same graph across the two hemispheres. In images, for example, we may have noise, or if we're collecting an MRI of a person, there's going to be noise, or the person may move, and we don't necessarily have an exact graph, a replication of the same graph across two different images. Okay, so this was just sort of an introduction of the problem. Now, well, I already wrote the notation here. So we're going to work with adjacency matrices, or matrices of size n by n. N is going to denote the number of nodes or vertices of the networks. And for simplicity, we're going to assume that the graphs are undirected, binary with no cell loops. So in principle, these assumptions can be relaxed by looking at different distributions, but we're not going to do this today. And what this implies is that the adjacency matrices are going to be symmetric with 0, 1 entries, and the diagonal is going to be equal to 0. So that just reduces the number of edges that we need to be looking at. This is a notation that I'm going to use for the set of permutations, pi n, all the permutation matrices of size n. And, well, this is what I explained already. So for each permutation matrix Q, we can find a permutation function associated to it, so that if we do this operation, Q trans plus BQ, what we're doing is just simply rearranging the rows and columns of the matrix so that the nodes are going to correspond according to this permutation. So this is an operation that we will be using a lot today. So just keep in mind this notation. Okay, so before starting doing some statistical inference, we need to define some models for the graph matching problem. And Mickey already talked about some of these models last week in his talk. So the basic model for constructing pairs of graphs that are related in some way or that look similar in some way is called the correlated Erdős-Rényi model, which basically the main idea here is that we are going to generate two graphs that marginally they look like an Erdős-Rényi, but they have some correlation between the edges, and we can control the correlation to make the graphs more or less similar. This was proposed by Pedersani and Grosslauser in, well, a version of this model was proposed by them, and there have been other versions of the model. And I will send the slides later, so if you want to look at the references, you can check them later more carefully. Okay, so in the correlated Erdős-Rényi model, the basic idea is that we're going to generate two Erdős-Rényi graphs with some correlation parameter rho. And we're generally going to take rho greater than 0, meaning that the edges are going to be positively correlated. In principle, it's possible to take rho less than 0, but then we need to look at the inverse of the graph, or like non-edges of the graph. But for simplicity, we're going to assume that rho is positive. So what this model proposes is that the marginal distribution of each of these graphs, A and B, is going to be Erdős-Rényi with parameters n and p. Or in other words, just this means that the probability that we observe an edge between I and j is going to be equal to p for I greater than j. And all of the edges are independent between each other, right? And same for b. And the joint distribution of the edges is going to satisfy that the correlation between Aij and Bij is going to be equal to rho. So if we look at the vertices of the graphs next to each other, basically we have two adjacency matrices with the correct correspondence. Each entry here is going to correspond to an entry here, and they are going to have a correlation equal to rho. So that's the main idea. So here you can see that when rho is equal to 1, this is going to reduce to the graph isomorphism problem because the two graphs are going to be exactly the same. And when rho is equal to 0, there is not going to be any information in common between the two graphs. So we can control how much similarity we want to have between the two graphs by changing the value of rho. Well, this is a very simple idea. I mean, we just need to define the marginal distributions and then define the correlation. There might be some issues in generating these random variables. I'm going to talk about this in a minute, but I wanted to mention that, I mean, in principle, there's nothing that prevents us to work with a similar idea in different types of models. For example, if we have community structure, we can put a stochastic block model distribution instead of an Erdős-Rényi distribution here. We can even look at inhomogeneous Bernoulli graphs with arbitrary probabilities on their edges, or even more general classes of graphs, like graphons, or even we can put a different distribution on each graph. So for example, in the Twitter versus Facebook example, we wouldn't expect to see exactly the same number of edges, or even the average number of edges across the two networks. Maybe one of the networks is denser than the other, so we can put a different distribution on the two, and just generate some random variables with some correlation. There are some issues with the correlation in this type of situations because we have, well, I mean, the correlation for Bernoulli variables doesn't work in the same way as Gaussian random variables, so we need to restrict the possible values of rho when we do this type of things, but I mean, in principle, this idea works in general situations. Now, when it comes to actually generating the graphs or analyzing algorithms under these particular models, looking at correlated Erdős-Rényi graphs is okay, but there are easier ways to analyze these problems. And there are some model generation procedures that have been proposed in the literature. So maybe the most common one is this idea of edge subsampling, which was actually the way Pedersani and Grosslauser introduced the Erdős-Rényi, correlated Erdős-Rényi model. And the idea here is that we are going to have three parameters, n and p, which are the same parameters for the Erdős-Rényi distribution. But then we have a parameter s, which is going to control the sparsity of the graphs. So the idea is that we start with a seed graph, G0, or a generator graph, sampled from some distribution, but in principle, this could be just the Erdős-Rényi distribution, G and P, this graph here. And then we're going to independently sample two graphs, G1 and G2, by subsampling the edges of this graph. So basically, for each edge of this graph here, existing edge in this graph, we're going to flip a coin with probability s. And if s is equal to 1, what's going to happen? The edge is going to remain. And if s is equal, and if the random variable is equal to 0, the edge is going to disappear. So in principle, this operation is only making the graph sparser. And the marginal distribution of the two graphs is going to be Erdős-Rényi, but with parameter p and s, p times s. So we can control the correlation by changing the values of p and s in this way. So that's one way of generating correlated random graphs. An alternative way, which I'm going to focus more on this one because, well, I'll talk more about the analysis of the algorithms in a minute, but an alternative way of generating graphs is by just fixing one graph as a deterministic network. So A is going to be kind of a parameter in a sense, well, or a given graph. And then we're going to apply a similar idea. We're just going to flip the edges of A with probability Q. So if there's an edge connecting the two, or basically for each pair of vertices, we're going to flip a coin. With probability Q, we're going to flip the value of the edge. For example, if there's an edge, we're going to remove it. If there's no edge, we're going to add it. And with probability 1 minus Q, we're going to keep A the same. So here you can see that when Q is equal to 0, we're basically preserving the same graph because B and A are going to be the same. So then this is the case of a perfect correlation and the graph isomorphism problem. When Q is equal to 1/2, we get a completely independent graph in the sense that all of these edges are going to be just Bernoulli random variables with probability 1/2. So these are the two extreme cases in this method. And well, one of the advantages of looking at the graph in this way is that basically we can plug in any graph that we want, and we can just focus on the structure of this graph and see how this affects the feasibility of solving the graph matching problem. So yeah, I'm going to talk more about this in a minute, but yeah, basically I just wanted to introduce the two ideas of generating graphs. Okay, so now the next question, now that we have the models, is how are we going to estimate the permutation matrix Q, right? So the problem is that we're given two graphs, A and B. They come from some distribution F. And well, in principle, in the graph matching problem, we're going to observe a shuffled version of B, right? The problem here is to find a permutation that relates A and B, right? So once we generate the two graphs, A and B, we're going to shuffle the edges by some permutation Q star, which is basically the one that aligns the vertices of the graphs. And our goal here, which is something that Keith mentioned in his mini course last week, is that given two observed graphs, we want to go back and estimate the parameters that generated these graphs. Right? So in principle, there are several parameters involved here. So there are parameters that were used to generate the distribution of these two graphs. But in graph matching, we don't really care about this distribution. This is like a nuisance parameter for inference. But what we want to do is estimate this permutation matrix regardless of the parameters that that generated these graphs. Right? So our goal is that given A and the shuffled version B tilde, we want to be able to infer Q star using some estimator Q hat. Right? So that's the problem. And once we have an estimator, we have two notions of recovery, or two ways in which we can measure how good the estimator is. On the one hand, we can ask for the estimator to completely recover all the vertices correctly with high probability or something. So the notion of exact recovery is basically saying that. So in the limit, as the graphs get bigger, we're going to have a probability approaching 1 that correspondences between the two the set of vertices are going to be the same. Right? So this is maybe too much to ask for some specific models, because you can imagine if the networks are very sparse, it's going to be almost impossible to match the vertices. If we have vertices with 0 degree, there's no information to match the correspondences. And even when we have just degree equal to 1, there's a high chance that this edge may be removed, and we won't be able to find the correspondence exactly. So alternatively, what we can ask is a relaxed version of this definition and just match a proportion of the vertices between the two graphs. So in this partial recovery definition, we are asking for a proportion epsilon of the vertices. So this function here, which is also something that I'm going to be using later, is just the Frobenius norm between the estimator and the true parameter here, or the true permutation. And basically, this is just counting the number of times that we make a mistake in estimating the correspondence between two vertices, right? So actually, this is going to be equal to 2 times the sum of the indicator that our estimator sigma hat of I is matching the vertex to the ground place, right? And this is equal to 2 because we're counting twice the errors in this function, in the Frobenius norm. When we look at the matrix, we have an error coming from here, but the same error is going to appear here. So that's why we have the 1/2 in the denominator, right? But anyway, so basically these are the two notions of recovery that we can ask. So in this case, there's probably more hope in models with low degree nodes. And we can even relax this definition more and maybe ask that only a proportion with some specific rate of the vertices is correctly matched. And yeah, so instead of requiring a linear proportion of the vertices. Okay, anyway, so I'm going to focus on the exact recovery definition today, but There are also works that talk about the partial recovery. But in order to simplify the notation, we can assume without loss of generality that the correct permutation that is linking the vertices of A and B is the identity, which basically this is just trivial to think of it as like, we're going to look at all the permutations, and in principle, the solution should be the identity in order to get correct recovery, right? So, I mean, we don't lose any generality by just assuming that Q star is equal to I, and that's going to simplify the notation. And then we can just work with A and B rather than B tilde. Okay. Okay, so the next question is, how are we actually going to estimate the permutation? So in statistics, we have basically the same ideas that we use all the time, which are maximum likelihood estimation or maximum a posteriori estimation, which given the model, we want to maximize the likelihood of the data, or we want to find the parameters that maximize the likelihood of the data. And basically what this is saying is that we want to find the parameters that fit the data the best, right? So this is the approach that we're going to take here. So, I mean, we can do this for either the correlated error ranging model or the channel corrupted model that I mentioned a few slides ago. So in particular, for the channel corrupted model, the likelihood, so remember that in this model, let me write it here. We have that A is a given graph, and B is going to be a function of A, where the edges are flipped with probability Q, right? So in this case, we can write down the likelihood function of this graph because the edges are independent as the product over all the upper triangular part of the adjacency matrices. And well, we can look at the given permutation Q, and we can see what's the chance that the correspondence between A and Q be Q transpose gives you the same vertex. And basically here, sorry, the same edge. And basically here, the probability that this happens is going to be given by this. This is going to be P to the indicator of these two edges being the same times 1 minus P to 1 minus the indicator, right? Yeah, so we actually, well, this is Q, sorry. So yeah, so we flip the edges. So if Q is equal to 0, we keep the edge. Yeah, so basically, so this is the likelihood, right? And alternatively, we can write this in this way. I can just use the Frobenius norm difference between, well, I can just look at this entry, AUB minus QB, Q transpose UB. I mean, basically, this is just a single number, but the point is that I want to write everything in terms of the Frobenius norm. And 1 minus the same thing. And when I take the product over all the possible edges of the graph, or the whole likelihood of the graph, U greater than B of this probability, this is simply going to be equal to Q to this difference A minus QB Q transpose in Frobenius norm, 1/2. So this is counting the number of differences that I have between A and the shuffled version of B, right? So I mean, yeah, this is just, we can write this as an indicator, but I'm going to be using this Frobenius norm notation, and 1 minus q, n for n minus 1 over 2, minus this Frobenius norm. So the point that I want to make is that basically, when we do this, it's kind of clearer to see that the likelihood function essentially only depends on this Frobenius norm difference, A minus Q V Q transpose, which is measuring the number of differences of edges between A and some permitted version of B, right? So basically, with this likelihood function, it's not hard to check that the MLE for the permutation under this model is going to be equal to the solution of this optimization problem, which is a very popular problem used in computer science and other areas to solve the graph matching problem in general. So even if we don't have a model, this is a loss function that is typically used. But under this particular model, the loss function actually coincides with the likelihood function. So this kind of suggests us that using this approach is good for a problem. We can alternatively write this loss function as the dot product between A and Q B Q transpose, or basically this is just taking the sum over all the products of the edges of A and the edges of B after flipping the rows and columns. But again, I mean, here it's also trying to maximize the similarity between the two graphs by trying to find the permutation matrix that aligns the correspondence between the two, right? And in general, I mean, this result not only applies to the channel corrupted model, it also applies to the correlated ER model under maximum a posteriori estimation. So if we put a prior of all permutations having exactly the same probability, we can show that the solution of this optimization problem is also going to correspond to this loss function. So, well, in principle, this is saying that this loss function is good. And also, this is telling us that if we're able to find the solution of this problem and the solution is correct, then we will succeed in the problem. And if the solution is not correct, then there's no hope in solving the graph matching problem for the particular set of parameters. And, well, I also wanted to highlight that this equivalence is not always true. For example, in the stochastic block model, the probabilities for the edges of A and B are going to depend on the communities. So then this loss function is going to look similar because this is still sort of independent edge random graph. But here, the weights of the block model are going to appear in the loss function. And I mean, this is in some sense similar to the situation that happens in linear regression when we have heteroscedastic versus homoscedastic errors. I mean, we can use just the usual least squares formulation, or if we have different errors on our data, well, we may use some different loss function rather than the least squares. But in principle, under these models with sort of like homogeneous noise, we can use this loss function, and that's fine. Anyway. Okay, so now the question here is, when are we able to solve the graph matching problem? And as a reminder, we're using the assumption that the true permutation is the identity, just to simplify the notation. And under this assumption, basically, and well, with the loss function that I mentioned previously, the solution of the graph matching problem is going to be correct whenever this loss function evaluated at the true permutation, which is the identity, is smaller than any other permutation, right? So if there's a permutation Q that has a smaller likelihood or a smaller loss function here than the identity, then we're going to get the ground solution. So we want to find under which cases we're able to obtain this inequality for all possible permutations different than the identity, right? So that's basically the condition that we need in order to check that the problem is solvable or not. So exact recovery is going to be possible as long as the probability of this event happening is converging to 1 as n is going to infinity. So the probability that the loss function on the identity is smaller than any other loss function for all possible permutation Q different than the identity. Well, actually, I forgot to write here different than the identity. But basically, yeah, so that's the condition that we need to check for exact recovery. And well, and similarly, I mean, we are not going to be able to solve exact recovery correctly if this probability is going to 0 as n goes to infinity, because that means that there's not going to be hope of finding the correct solution if the graph size gets bigger and bigger. Okay, so now, what are the results for this problem? So in the correlated errors ranging model, there are two main challenges for matching the two graphs. On the one hand, we have the sparsity of the graphs. If P is too small, we're going to have a lot of vertices with no edges, or even with very few edges, and there's not going to be much hope in identifying the correct correspondence because, I mean, if there's no edge for a vertex, then we cannot really tell the difference between two of them. If there are a few edges, it's very easy to perturb them when we do any of the sampling procedures. For example, here if we do edge subsampling, it's likely that some of those may be removed if S is sufficiently small. And I mean, the other challenge, of course, is the correlation. When the graphs are more correlated, when S is equal to 1, it's still possible to match the two graphs as long as we have enough edges. Again, we still have the sparsity issue that we need to be careful about. But yeah, in principle, if the correlation is large, we should be able to solve the problem. If the correlation is too small or even equal to 0 or close to 0, then we won't be able to do it. So there are results that characterize this threshold for exact recovery that were proposed in 2016 and then were refined in 2017 by Kulina and his co-author, which I forgot the name, but I have the references at the end. So basically, these results say the following. So we consider here the edge subsampling model in which, again, we take a generated graph with Erdős range distribution, and then we subsample the edges with probability S. So we remove some of them. And the result says that exact recovery is going to be possible as long as this happens, right? So the probability and the correlation are sufficiently large relative to n and relative to log n, right? So another way of looking at this result is just saying that if P times S squared is greater than log n over n plus some small constant, then we're going to be able to solve the problem. And if this is not the case, then the problem is not solvable, right? Yeah, so basically, for example, here, if we keep the correlation constant, this threshold for the probability is sort of similar to the threshold for connectivity in an Erdős range graph, which has been discussed by Dieter on his course in the past week and this one. And similarly, when P is constant, the threshold for the correlation is on the order square root of log n over n. Right? So yeah, so these are the two parameters that control the difficulty of the problem in the correlated Erdős range model. Okay, so I'm not going to do the proof of this result exactly, but I'm going to focus on the other model that I mentioned. Let me go back in a minute. So yeah, I'm going to focus on this model, which is very similar, and then I'm going to show you how to connect this, the results for this model to the correlated ER. And the proof techniques are very similar, so hopefully with this one would be easier to show the result. But essentially, as a reminder, in this model, we take a graph A. We take some probability Q. Actually, this should be Q instead of P. But we take some probability Q, and then we flip the edges with this probability Q. right? So if Q is large, then if Q is close to 1/2, then we get two independent graphs. If Q is close to 0, then we get the same graph. Okay, so let me move back here. Okay, so now we focus on this model. We have A and we have B, which is a noisy version of A with some probability Q. So the main difficulty of this problem is to make sure that when we flip edges with probability Q, we don't destroy that many edges, right? So we are still able to tell when we have the correct correspondence. In the extreme scenario where we just want to be able to do the graph isomorphism problem, for instance, we can look at this function here. We can look at A. We can permute its rows and columns and compare with A. And basically, if there are two situations in which this function is equal to 0, we won't be able even to solve the graph isomorphism problem, right? Because that means that there are automorphisms in the graph, and there's no hope in solving the problem. Now, when we have noise, we need even more signal in order to tell the difference, but we still need to measure the similarity between A and some permuted version of itself. So here I have some figures to illustrate this issue. So for example, when Q is equal to 2, we can look at the permutations of size 2, or basically we just take two vertices of the network and we permute them. So this is A, this is QA, Q transpose. We flip these two vertices, and then we measure the similarity between these two, right? So if we perturb the edges with this probability Q, and we look at the loss function, if these edges here, for example, are removed with probability Q, then it's going to be hard to tell the difference between the solution with Q and the solution with the identity, right? So in other words, we need a large value here so that there's a small chance that the sufficient number of edges are going to be perturbed, and we can still find this correspondence, right? So that's the main difficulty in this problem. Here's another example with 3 vertices. And I mean, as you can see, as you get more and more vertices, there are more edges that are being shuffled. So here, I mean, basically for small values of k, it's harder to tell the difference between A and a permuted version of it. Or it's more likely that a perturbation Q is going to remove some edges that tell us the similarity between the two graphs. Right? Okay, so that's basically the main quantity that we need to focus on. Okay, so here is the result for this model. So we consider a sequence of networks and parameters Qn. And we're going to look at the sequence as n goes to infinity. As I mentioned in this slide here, we need to look at different sizes of the permutation, because different sizes are going to have different magnitude of edges that are being shuffled. So we're going to define pi and k as a set of permutation matrices that permute exactly k vertices. So for k equals to 2, we only move 2 rows and columns of A, and so on. And we're going to assume that Qn is sufficiently bounded away from 0, but it's also bounded from 1/2. Right? So 1/2 is the case in which the two graphs are completely independent. So under this model, we have the following result. Here, we're going to be able to match the vertices of the two graphs correctly, as long as this version of A with a permuted version of itself, QAQ transpose, has sufficiently large number of differences, in particular this large number of differences. And you can see here that it depends on the number of vertices that are being shuffled, as well as the number of nodes and the probability of perturbing the edges Q. So if the minimum of overall the permutations is greater than this, for all values of k, then we're going to be able to solve the problem correctly. And conversely, if we are able to find order of n disjoint permutations such that this is not true, or in other words, I mean, this quantity here is upper bounded by log n over some function of the probability of perturbation, then we're not going to be able to match the vertices correctly, right? So basically, a thing to notice here is that essentially the main threshold that is governing the difficulty of the problem here is log n over this function of the probability of perturbation. So this sort of tells us how much tolerance we have for a given graph of perturbing the edges. If we have a graph that is more irregular, then we can choose a higher perturbation probability Q, and we can still recover the correspondence between the vertices. Okay, so that's the result. Well, so now I'm going to give you an overview of the proof of this result. And well, as I mentioned, I mean, this is in some sense slightly more general than the correlated ER model, because here you can plug in any model that you want for A and look at whether this model actually satisfies that threshold. So I'm going to show you later how to connect this to the correlated ER model. But I mean, in principle, we can just look at A and see how this affects this feasibility of matching the vertices. Okay, so basically this is the idea for the proof. So I'm going to define this quantity, x hat q, which is basically going to measure the loss function evaluated at some permutation q, some arbitrary permutation, so A minus q b q transpose, minus the loss function evaluated at that true permutation, which we define as the identity. Right? So basically, whenever xq is greater than 0, for all permutations q different than the identity, that means that the graph matching solution is going to be correct. Or in other words, q hat is going to be equal to the identity, right? Which is the permutation that solves the problem. I mean, what I'm saying here is that if this is positive, it means that the ground permutation has higher loss function, so we would choose this permutation, and then we need to verify this for all possible permutations, right? And similarly, we can define a population quantity, xq, which is the quantity that I mentioned earlier, A minus QAQ transpose in Frobenius norm, which is measuring how different is A from some permuted version of itself, right? So the larger this value, the smaller the chance that we get too many perturbations that destroy the solution of the problem. And in order to look at the difference between these two quantities, I'm going to define delta Q, which is the set of edges, or the set of node pairs in the network, I greater than j, such that A is different from the permuted version of itself on the edge ij, QAQ transpose. And that Aij is equal to Q transpose BQ Aj. So basically, this set delta Q is counting the bad edges, the ones that destroy the structure of the problem, because here what we're saying is that when we permute A, we get a mistake, but the randomness in B is going to correct that mistake, and then it's going to make it look more similar to A. Right? So those are the edges that we don't want in order to be able to recover the solution. So the first claim is that x hat q, the difference between the loss function at q and the true permutation, is equal to xq minus 2 times delta Q, right? So basically, this is a population parameter that only depends on A. This is the noise on the edges, and these are the bad edges. And from here, we can just focus on the randomness in this random variable and see how likely is that this event doesn't happen. Right? So that's the first claim. And just using properties of the Frobenius norm, we can show that we can write this part here as A minus Q transpose AQ plus Q transpose AQ minus Q transpose BQ. Right? Which is just the first part of X hat Q. And this is basically going to be equal to this quantity here, XQ, plus A minus B. So I can take these two terms, but the Q cancels out because it's a permutation matrix, and the permutations cancel out with the Frobenius norm. Oh, well, basically, the permutation is an orthogonal matrix, and the Frobenius norm has the property that orthogonal matrices cancel out. So basically, this part here is just equal to this. And we have the term that contains A minus Q transpose AQ and Q transpose A minus B times Q. Right? So this is the cross term between this part and this part. Right? And here, this part is XQ. So the only thing that remains to check is that this part here is actually equal to delta Q. But by looking at the definition, this is not hard to see because here, on this first part of the definition, we're counting the places in which Aij is different from AQ transpose. So basically, these are going to be ones in this part of the function. And then, for instance, if this is equal to 1, if the corresponding entry of A is equal to 1, what this means is that the corresponding entry Q transpose BQ is also going to be equal to 1. So then this is going to create a 1 here. And if this is 0, it means that the corresponding entry here is going to be 0, but this is going to be equal to 1. Yeah, so this is also going to be counted in this way. So, in principle, we can just make sure that these two quantities are the same. So what this means is that this whole thing is equal to XQ plus A minus B minus 2 times delta Q. So that means that once I subtract this part here, this is equal to this. Once I remove A minus B in Frobenius norm, I'm going to get that X hat Q is equal to XQ minus 2 times delta Q, right? So that's the first thing. So once I have it in this way, the next thing is to check that delta Q is a binomial random variable with parameters XQ and a probability little qn. Okay? So the probability of perturbation. And this is also easy to see from the definition because here in this definition, we're counting the number of times that A is different from the permitted version of itself, which is just equal to XQ. And then the chance that this is equal to 1 is basically the chance that A gets perturbed with probability Q, right? So this is the parameter of the binomial. So once we have these two things, we just need to check the probability that the graph matching function is incorrect, or the probability that the loss function is incorrect, meaning that what's the probability that x hat q is less or equal than 0, in which case q is going to be at least as good as the true solution, which is the event that we don't want to happen, right? Well, by this definition here, because x hat q is equal to xq minus 2 times delta q, this probability is equal to the probability that delta q is greater or equal than xq over 2. Right? So basically, I mean, just by substituting this function and then rearranging things. And we know that this is binomial, right? So actually, this is an easy calculation. Let me go back to the slides here. So here I have a concentration inequality that I'm going to use. I'm not going to look at the proof of this, but this is a result that we can just use. So for a binomial random variable, which is a function or with parameters m and q, we can upper bound the probability that this deviates from this quantity, n times m, with an exponential function that depends on the number of terms in the binomial distribution, or the parameter m, times the relative binomial entropy, which has a closed form solution in this particular case. Right?
I guess at A there should be 1/2, right?
Oh, here?
Yeah. Because you wrote the entropy of 1/2 Q.
I see. Yes, thank you. Yeah. Yes, sorry, I will fix that in the slides later. But yeah, so using this concentration inequality, we can upper bound this binomial random variable with negative xq, h of 1/2 times q n, which, I mean, I can look at this result, but for simplicity, I mean, we can actually just directly use this in the theorem, but for simplicity, we're going to use this lower bound on the relative binomial entropy because, well, this is a bit more intuitive. And when q is far away from 0, these two are about the same order. So then we can write this as the probability. Oh, sorry, this is not probability. This is exponential function. This is negative 1/2 xq times 1/2 minus qn squared. And now, if we look back at the conditions in the theorem here, so xq is basically this quantity here, right? Well, xq is lower bounded by this quantity because xq is for a given permutation q, but we have this lower bound because this is the minimum over all possible permutations of size k. So if we just apply this inequality, we're going to get that this is upper bounded by negative 3k log of n, which is 1 over n to the 3k, right? So that's the probability that a given permutation q creates a mistake in the solution, or basically that this permutation q is better than the identity permutation, right? Now, we need just to take a union bound over all possible permutations. So we want to bound the probability that there exists a permutation q different than the identity, such that x hat q is less or equal than 0. We can take a union bound over all possible permutations of size k. By n k. This probability, k is equal to 0, and then we have a summation over k. We have an upper bound for this quantity for all possible values of q. So this is, well, actually, this is 1 over n to the power of 3k. And we just need an upper bound on the number of permutations of size k, which is basically this quantity is upper bounded by n to the power of k, right? So we're just flipping k vertices. So for each of, as worst case scenario for each of these k vertices that we're flipping, we have n possibilities. I mean, we have less than that, but just as an upper bound. So this is equal to, or this is upper bounded by 1 to the n cubed, which goes to 0 as n goes to infinity, right? So basically, the probability of making a mistake is going to go to 0, and then we get correct recovery of a permutation. Are there any questions or comments or anything at this point? So basically, the main idea here is just to upper bound this event, the event that there exists a permutation queue that has better loss function than the identity. And we just need to measure the number of mistakes needed for this event to happen, which has some bounded probability. So it's a very low chance that this happens for any possible permutation. So this proves the first part of the result. So I'm not going to go into the details of the second part, but just to.
Can I just ask a question? So these conditions, as you said, is a condition on AN, and it's kind of deterministic,
Right.
But if you take AN to be the adjacency matrix of the other training graph, so how large do you need P to be for this matrix?
Yeah, that's a great question. Actually, I have a follow-up slide here with the result. Yeah, I'll talk about this in a second, but yeah. So with Erdős range, yeah, we basically need to look at a bound for this quantity. Or I mean, now we can put a distribution on A. Yeah, so now we want the converse result. We want to show that if we have enough permutations Q such that this upper bound doesn't work, or basically there are not too many differences between A and a permuted version of itself, then we have a high probability of making a mistake, right? So the idea here, once again, we need to look at this quantity, x hat q, because that tells us whether or not a given permutation q is correct. So we want to look at the probability that x hat q is less or equal than 0. Which, remember, this is a binomial random variable. Delta q greater or equal than xq over 2. And, well, just by looking at, well, the binomial is sum of independent random variables. So intuitively, we can look at this quantity, delta q minus its mean, which is xq times little qn, the probability of a mistake. This event is superbounded by xq and half minus q n is lower bounded by this. So by looking at concentration of sums of independent random variables, we can lower bound this for sufficiently large n as c times the exponential of 1/2 of log n. I mean, essentially, you can think of this as this behaves kind of like a Gaussian distribution. So delta Q is going to be closer to its mean than this quantity for sufficiently large n. So we can upper bound, we can lower bound this probability. And now we just need to look at the random variable Zn, which counts out of this n permutations that we have, how many of them are incorrect, or how many of them are giving us a better likelihood than that true permutation. So this is the event in which we count x hat qi is less or equal than 0 for I equals 1 to n, right? We can lower bound the expectation of this quantity by using this inequality. I mean, these are just indicator functions. So we can lower bound this as c times n exponential of negative 1/2 log n, which is much bigger than 1. So, I mean, in principle, this random variable is likely to happen because the expectation is much greater than 1. So in order to complete the proof, but I'm not going to do the details here, but basically we can look at the second moment method to show that the probability that Cn is greater than 0 is equal to 1 minus little o 1. Right? So we would need to look at the second moment of Zn. And the thing here is that because we are taking these joint permutations, meaning that every permutation here in this set is permuting a different set of vertices, we have more independence between them, so that allows us to look at the interaction between terms in this function. So we can look at the second moment of Zn, and by using the second moment method, we can show that this probability is large. So there's a high chance that one of these joint permutations is going to be incorrect with respect to the true permutation that solves the problem. So any questions or comments or anything? Okay, so, well, now to answer Roberto's question about what happens with the Erdős-Rényi model. Here I have a result for the inhomogeneous Erdős-Rényi model, which is basically the same thing, but now we have a potentially different probability for each edge of the network. So we encode all of these probabilities with Pij. And I mean, this P can be arbitrary, but in order to give a concrete result, we're going to assume that the entries of P are bounded away from 0 and 1 with some constant alpha n. And basically, this alpha n is going to control the difficulty of the problem. In a similar sense, the Erdős-Rényi model. So once we have this result for deterministic A, what we need to do is check what's the probability that this lower bound here is satisfied. So basically, we can now use this distribution of A. The entries are random variables with probability P encoded in this matrix. And we just need to check what's the chance that this event is greater, or this event happens, right? And we want this event to happen with high probability. So here, I'm just going to show a concentration inequality that gives a result for this model. So I'm going to use a lemma by Lisinski et al. 2016, I think. And basically, this lemma says that the probability that in homogeneous Erdős Rényi model with exactly those conditions, P is bounded away from 0 and 1 with some parameter alpha n, the probability that an minus a permuted version of itself is less or equal than alpha n times k times n over 3 is upper bounded by 2 times exponential of negative alpha n squared k n over 120, right? For n sufficiently large. Yeah. So, I mean, well, basically now the entries of A are random by looking at this. This is basically going to be a sum of random variables. And I mean, I'm not going to do the proof, but one intuition here is just to see that when you permute k rows of this adjacency matrix, this part is going to remain the same, right? So we only need to look at sort of this rectangle and this square here. But, well, this has size k. We're using a permutation Q in P and K. So we're permuting k rows of this adjacency matrix. And, well, this has size n. So basically, we have about n times k random variables in this function. So that's why this upper bound is on the order of k times n times alpha n, which is the probability. Sure. So just applying this concentration inequality, we can directly check. I mean, using exactly the same idea as in here, we can take a union bound over all possible permutations and upper bound this probability. And basically, we're going to see that if we use this result, if we use this condition here, the probability is going to be high of satisfying the conditions of the theorem. So basically, we can confirm that we can recover the correct unshuffling permutation with high probability in this case. So now, going back to Roberto's question, comparing this to the Erdős Rényi model, if we look at the fixed probability bound alpha, so let's say assume that alpha is constant, these two conditions are exactly correspond to the previous result that I showed for the correlated Erdős Rényi model. We can think of this 1/2 minus Qn as the parameter S in the correlated ER model. So if you remember, this was on the order of square root of log n over n, which is great. The problem here is that the alpha n that we have has a higher order. Well, actually, if you remember, for a fixed constant S, actually, let me go back here. Yeah, so for a fixed constant S, P was like of the order log n over n. So in this case, for the Erdős Rényi model, this condition is not sharp because, I mean, this applies for a general probability matrix P. So when all the entries of P have exactly the same value, it's possible to get sharper results using a different concentration inequality. But here, because we're just looking at the lowest value, alpha n, we get a slightly bigger order. But yeah, but in principle, by analyzing this probability more carefully for some Erdős Rényi model, we should be able to get a similar result like the previous one. And yeah, so there are other results for different random graph models. For example, we can obtain a similar result for random regular graphs and other things, but yeah, I'm not going to talk about those today. So yeah, so basically, that's most of what I wanted to mention about the theory. So now I still have about 5 to 8 minutes. So I'll just cover very quickly about the remaining things. So, okay, so now we have a result that tells us when can we match the problems statistically. When can we match the graphs statistically, right? But, I mean, the problem here is that solving the graph matching loss function or finding the best permutation curve, it still requires to optimize over all possible permutations, which is computationally infeasible. So we need some optimization methods or some other ideas that allow us to do that more efficiently. So I'm just going to talk about a few of these methods in the remaining of the time. So yeah, in principle, solving this problem is not feasible computationally, or there's no known algorithm that can do that. One potential idea which was proposed by Lisinski et al. In 2015 is to relax the set of permutation matrices to the convex hull, which is the set of doubly stochastic matrices. Or in other words, these are the matrices D, such that the sums of the rows and columns is equal to 1. And in this case, we get a continuous relaxation of the problem. We don't need to optimize over permutations. We need to optimize over a continuous set, the doubly stochastic matrices. And it's possible to solve this problem. The issue is that this is still non-convex. So it's going to depend on the initialization or whether the loss function is nice or not. But yeah, in principle, we may need to restart multiple times or find a good initialization in order to obtain the best possible permutation in this scenario. Actually, in this paper, well, actually, I don't know if it's 2015 or 16, but it's the same paper here, the one that uses this inequality. But they show that using a convex relaxation of this problem, of the graph matching problem, the solution is going to be inconsistent. So convex relaxations don't work for this problem, in principle, or at least one based on the doubly stochastic matrices. So, well, now coming back to the example that I showed you at the beginning, I basically discussed two methods. Well, you mentioned two different methods for solving the problem. One was to try all the possible permutations, which is what we have been doing so far. The other thing is to try different properties of the graphs and explore some ideas in order to see whether we can find a correspondence. So there are methods that use exactly those ideas. So we can use a spectral information. This is related to the spectral method that I mentioned at the beginning. We can look at the eigenvectors of A and B and find a similarity between the two. The problem here is that this is not an exact matching, so they are not going to be exactly the same, but under some conditions, it's possible to show that looking at the eigenvectors with some weights and some other functions of them, the correct permutation can be obtained efficiently, meaning with a polynomial time algorithm. We can also look at the degree profiles, which is similar to the idea in the toy example. We can look at a node and the degrees of the neighbors and try to match according to what's the most similar node with those degree profiles. And there's also some recent work which, to the best of my knowledge, is the one that has achieved the lowest correlation so far for matching graphs in polynomial time, which basically looks at subtrees of the network. So you look at one vertex and look at all the possible subtrees with some particular family, and they are able to show that as long as the correlation in the ER model is greater than alpha, which is 0.338, or this is a constant that appears in combinatorics, it's possible to solve the graph matching problem. So the thing to notice here is that efficient methods only work up to constant correlation, whereas the statistical limits of the problem have correlation going to 0 at some rate. So there's still this gap between efficient methods and computational methods, but there are no results that establish yet where is this gap between the two. And yeah, I also wanted to mention that there's a zero graph matching version of the problem where we have a known correspondence between some of the vertices, and this can be used to solve the problem more efficiently, either by starting with those vertices and then extending the set of vertices looking at the seeds, or by solving the combinatorial problem, but with the use of these seeds, the solutions are typically more efficient. If you want to implement graph matching in your computer to do some simulations or to try some things, there's a package in R that was developed by Daniel Sussman and his student at Boston University who called iGraphMatch. And yeah, that's one of the packages that I know in R that works with this problem. And yeah, just to conclude, some additional ideas and open problems in the area. So, I mean, here I mostly focus on ER models or independent edge models, but I mean, you can think of these ideas using different random graph models, for example, geometric graphs, preferential attachment, or graphs with power law degrees. And another interesting idea is to look at situations in which the distribution of the two graphs is not the same. So once again, if we have a Twitter network and a Facebook network, maybe one of those is denser than the other, so we don't necessarily want to impose the same distribution, and that's basically going to create issues with the loss function, so we need to look at different loss functions or different methods for solving this problem, or even different models that can be useful for this. We can also look at bipartite data. For example, maybe we have a network of people, let's say a social network of Facebook or something, but we also know whether those persons visited some places. Maybe something that Google Maps has or something like that, right? So we know that person I visited place X, Y, and Z, and person J visited place Z, for example. And then in this case, the two networks, I mean, we cannot use the same tools because we don't have a correspondence between the edges, but we can develop some models that connect one of the networks to the bipartite graph or something like that. There are some ideas that merge community detection and graph matching, also to incorporate attributes in the data, like covariates or other additional information in the vertices that can be used to match graphs more efficiently. And yeah, another question is what happens when you don't have exactly the same number of vertices? So maybe you want to match just a small subgraph to a bigger graph, or even graphs with different number of vertices, and maybe not all of them correspond to each other. So yeah, this is also a potential idea. So yeah, so that's basically all. Here are the references, and yeah, I'll send you these slides later, or I'll send those to Roberto, and he can distribute them later. So thank you.